A bullet of mass 20 grams moves with the speed of 18 meters per second and strikes a block of mass 0.54 kilogram initially at rest. After the collision, the bullet becomes embedded into the block. So what is that? That's a perfect inelastic collision right there. The block is attached to the end of a spring with the spring constant 80 newtons per meter. What is the initial kinetic energy of the bullet? What is the speed of the bullet block system after the collision? What is the kinetic energy of the bullet block system after the collision? What is the maximum elastic potential energy when the block comes to rest? And then what is the maximum compression of the spring? These two are the same thing, right? And what is the period of oscillations? What is the initial kinetic energy of the bullet? Well, that's just Ke is 1/2 mv squared. The only trick is right here. Okay, so you have 20 grams. You need to convert that to kilograms. So you have to move the decimal place 3 to the left. So you go 1, 2, ran out of numbers, so let's quickly throw a 0 in there. 3. So the answer is 0.02 kilograms. Put that in, square the velocity, and you get 3.24 joules. What is the speed of the bullet block system after the collision? We cannot use conservation of energy here because we have a perfect inelastic collision and Ke is not conserved. However, we can use conservation of momentum. The 1, that represents the bullet. The 2, the subscript 2, is the block. And the primes give you the velocity after the collision. So the initial condition is the block's not moving. So m2v2 goes out. So on the left side, we just have m1v1. Then on the right side, it's m1v1 prime plus m2v2 prime. But what do we know about v1 prime and v2 prime? The bullet is embedded in the block, so they're the same. So we can get rid of the subscript and just call it v prime. So we now have m1 times v prime plus m2 times v prime. Factor out the v prime, and we have m1 v1 is m1 plus m2 times v prime. Now we want the speed of the bullet block system after the collision. So that's v prime. So it's real easy to do this one. Divide both sides by m1 plus m2. m2. Same thing over here. Kind of ran out of room. But we get v prime is m1 v1 divided by m1 plus m2. We put in our masses. Be sure to convert grams to kilograms. And it looks like we just have to do it for the bullet. The block already is in kilograms. We have a velocity, the initial velocity of the bullet, and then the final velocity of the bullet block system after the collision is 0.643 meters per second. And not really the final velocity, but it's the initial velocity once the bullet gets stuck in the block and starts to compress the spring. What is the kinetic energy of the bullet block system after the collision? It's going to be the total mass of the bullet and the block times the velocity of the bullet block system right after the collision that we found on the previous slide. So here's our two masses. Here's our velocity. Make sure you square it. And then we come up with a kinetic energy of 0.116 joules. What is the maximum elastic potential energy when the block comes to rest? So let's use a work energy equation here where the initial energy, which is all in, put the bullet here, the bullet block system when it starts moving, right before it compresses the spring, the only energy you have is Ke. There's no work done. We're assuming a perfect spring that has no friction, so there's no external work, so this term goes out. And when the block comes to rest, that means the block has squished this as much as it can before what? Before the spring shoots it out this way. And at that point, with no kinetic energy, all you have is elastic potential energy. So the maximum elastic potential energy will be the initial kinetic energy, which was 0.116 joules of the bullet block system. What is the maximum compression of the spring? We have EPE is 1/2 kx squared. The maximum compression is going to be this x term when we use the maximum EPE. We'd like to solve for x, multiply both sides by 2 over k. And you see that comes here. times EPE. Whatever you do to the right, you have to do to the left. But we want x, not x squared, so that's why the square root is here. Put the numbers in. 2 times 0.116 joules, which is the maximum elastic potential energy, divided by the spring constant, and we get 0.0539 meters, or 5.39 centimeters. To go from meter to centimeter, move the decimal 2 to the right. So that's 5.39 centimeters. What is the period of oscillations? Well, we're going to use the equation for the period of a mass spring system, which is 2 pi times the square root of m over k. And the only trick here is make sure you use the combined mass of the bullet and the block. Divided by k, take the square root, multiply by 2 pi, and you get a period of 0.525 seconds.